Yes, so I want to share some of the excitement we are having researching the Milky Way. And so I always like to start talk like this with a view of the Milky Way and as seen in the night sky. This is a view from Joshua Tree National Park. And this is really exciting because other than just being a beautiful view of the night sky, it also is a product of billions of years of cosmic evolution. So what in my research life I try to do is trying to kind of decode the messages about the universe and the cosmology that are encoded in this beautiful display of the night sky. And so we think it all started something like this. So this is a view from the illustrious TNG 50 simulation forming one isolated Milky Way-like galaxy, which I think it started in a fairly uniform universe, where then over this region started accreting more matter, and shown in the main window is the gas forming kind of in these filaments, forming into a galaxy that's forming at the center. And here in the bottom, you can see the zoom in of the gas on the right, and then the starlight on the left. And on the very left is kind of the underpinning of this all. So this is the dark matter view of the same system. You can see that as kind of specific clumps of gas associated with dark matter are coming in, like the galaxy gets bigger and forms like this by redshift 1.5, this very intricate display. And so this is kind of what we think the universe looks like or how it evolved. And then the question is, can we disentangle this process by studying the Milky Way? So obviously, like as we see this movie playing forward, there are these smaller dwarf galaxies joining in to build one bigger galaxy. And the question is, how much of this process can we decode, and what can we learn about those early galaxies by studying the Milky Way that we see today? There's kind of a combination of all of these individual building blocks. And this is a process that is still going on. So I guess it was the first confirmation that we had was that we have satellite galaxies around the Milky Way coming in. And some of them can also get tidally dissolved to form like these intricate structures called stellar streams. And the very low mass ones, for example, this is an example of a globular cluster, tidally dissolved to form a stellar stream, can also help us to understand the structures that we do not see in light. So there are kind of these two parts of this hierarchical buildup. We have the dark matter building up and the dwarf galaxies building up. And so dwarf galaxies we can kind of see shredded in these stellar streams, or we hope to see them. But then what happens with the dark matter? And so it turns out that for this very thin stellar streams, we do have using them to detect dark matter. So this is from work a couple of years ago where I modeled such stellar stream, and we think what happened is that it encountered a compact object such as dark matter subhalo that passed by the stellar stream and then kind of kicked some stars out from their original orbits to produce like this gap and a smattering of stars around it that we, like when we kind of zoom in at the present, see displaced from the main track of the stream. So it seems like that this outer regions of the Milky Way would be like a good hunting ground for this cosmological evolution. We would have both the kind of stellar debris, which will be telling us about galaxies, and also the same structures can tell us about dark matter substructure. And so this is kind of like shaping up to be an interesting experiment, but there are some complications in this picture. And this is that it is looking very kind of non-trivial in the sense that Milky Way is still evolving. It's not a kind of experiment like in a lab setting that we can control all of the knobs, but rather, this is what we have. And what we have, I'm showing here, is a view of the outer part of the Milky Way galaxy. So the density map is the density of K-giant stars between 60 and 100 kiloparsecs. And you can see that it is very non-uniform. So this is already like the first clue that something is kind of happening here. And if you see like this strongest over density, is kind of connecting to the large and the small Magellanic Cloud. Turns out that this is exactly what we would predict as a response of the Milky Way galaxy on the impact of LMC. So you see some stars kind of getting closer to the LMC orbital path, sort of in a sort of wake sense. So this is the path that LMC passed and attracted stars from the Milky Way halo along this path. And it also, in addition, shifted kind of the entire mass distribution or the center of mass of the Milky Way, producing this overdense region on the opposite side of the galaxy. So it looks like if we were to do this cosmological experiment, we'll need to disentangle many different things. And the question is kind of, will they affect what we learn about, say, the galaxy formation or dark matter substructure? And this is work that I wanted to show by Bridget Segovia who did this summer at Carnegie Observatories, who want to ask the question of what is the distribution of dark matter subhalos in the Milky Way-like galaxy, and a simulated Milky Way-like galaxy that does have an LMC. And so what she did is take a simulation run by Ethan Nedler, who is a postdoc at Carnegie and USC, and plot the positions of dark matter subhalos on the sky. So this is shown over here. And if you remember from the location over here, we have LMC in this part of the diagram. And again, here in the simulation, there is a very massive dark matter subhalo, kind of an LMC analog. And you can see that the distribution overall, because of the presence of this one subhalo at the moment, is very inhomogeneous. And so then our question of kind of how much can we learn about substructure from stellar streams will depend on which stellar stream we are looking at, because we have a number of stellar streams on the sky in different regions of the galaxy, probing different on different orbits, and then have different probabilities of encountering different dark matter subhalos. And so this is something that Bridget just yesterday calculated for all of the streams. What is the probability of encounter, or what is the closest distance to all of these subhalos? And so this is just to kind of show that the Milky Way is fast becoming like a very complicated laboratory. And the questions that I want to ask are kind of ambitious in that regard. So I want to know what the nature of dark matter is. I want to know if there really are subhalos roaming around the Milky Way halo. And ultimately, this kind of boils down to the question of what is the universe made of, because we think that dark matter is most of the matter in the universe. And then more broadly, the question of how did the Milky Way form, what are the building blocks of the galaxy, ultimately comes down to the question of how do we come here? So which is a very fundamental question that touches many areas of human endeavors. And kind of asking like just a map of stars, like these questions seems like very ambitious. And really the only hope of answering these questions was provided fairly recently, only a few years ago, by the Gaia mission, which provided us with more than just positions of stars today, but rather measurements of their velocities. And so this is a movie produced by the Gaia team. I'm not sure very well, but anyway, you'll see like objects starting to move. So Gaia measures positions of 2 billion stars and continually measures their positions so that you can measure the components of motion in the sky, and for the brightest stars that are shown over here and kind of closest to the sun, also radial components of motion. And so what this allows us is to calculate the orbits of these stars and see kind of not just where they are now, but where they were before. And obviously, so many of the questions that I touched upon before had to do with the outer parts of the Milky Way. So I wanted to know not just how stars move close to the sun, but also throughout the galaxy. And this is what I've been working on for the past few years, is in providing most of these measurements from using the hectoshelf spectrograph on MMT as a part of the hectoshells in the halo at high resolution survey, or H3 for short. So our goal has been really to map the outer parts of the Milky Way, and the hectoshell field of view is 1 degree. And so what we did, starting in 2017, is kind of go from like this very high latitude fields, and the color is showing the time of observation, and then not really targeting anything, just kind of placing on a uniform grid spaced by 3 degrees different fields and kind of filling out the footprint. And we had some stop time during the pandemic, but then picked up really last year a lot. And so at the moment we have basically covered all of the southern sky, and are working at our southern sky observable from Arizona, and then are working on the northern sky as well. And so in each of these pointings, we obtain spectra of 200 stars. They're in magnitudes between 16 and 18, so which is fainter than what Gaia will be providing radial velocities and spectra for. And this is distant stars. So only other selection we make is that these are stars with parallaxes smaller than 0.5 milliseconds, so farther away than 2 kiloparsecs. And the big part of the survey, or the success of the survey, is thanks to the work of Phil Cargill, who has been analyzing this spectra to measure precise radial velocities. So this is a high resolution or instrument, or at least, well, yeah, I know there are people studying Mars and exoplanets, so maybe for them this was not very high resolution, but in a dynamic sense it is 30,000, and so that allows us to measure radial velocities with a precision better than 1 kilometer per second for basically all of our sample. And here is just one example of the spectral region that we are using in the magnesium B triplet. So these are these main tree lines over here, and the spectrum is in black, and the purple is the fit, which shows why we can measure the velocity so precisely. But then the second part of the pipeline is that Phil combines the spectroscopic information with broadband photometry that is available for all of these stars. And in doing so, we can also measure what is the total luminosity output of the star, and therefore calculate what the distance is. And so Gaia distances are really very good close to the sun, but then out in the halo are not very good. And so by even though the distances we measure are not like the most precise at all, they're way better than Gaia parallaxes, even at 20% uncertainty. And so now with this kind of view of or these 2 extra measurements, we can calculate orbits combined with Gaia sky positions and proper motions for all of the stars in our sample. And here is a view of kind of what they look like. This is a sample of 100 stars from H2 survey, color coded by their distance. And so you can see that some of them go very far away, even beyond 50 kilometers. And as I'm calculating the orbits, kind of the timer is going up on top. You can see that some of them are moving very fast. And this information was used first to calculate what is the total mass of the Milky Way. Turns out it's fairly massive. It needs to be more massive than 29 times 10 to 12, which is the kind of first lower limit placed by the historicity, by really analyzing like the outliers of this distribution, and then by modeling this full distribution. We have a actual constraint of like 1 times 10 to the 12 solar masses, and which is much more than the stellar mass, obviously, in the containing the disk. It shows that this is a very dark matter dominated region of the galaxy. And so this is very interesting, kind of shows that we are peering to this new regime of the galaxy, but it also shows kind of what we could find in. And so if have kind of a good eye might have picked up that the distribution of these orbits is not spherically symmetric. There is looks like there are some stars that are kind of moving on similar orbits. Turns out that these stars are all stars that have been tidally stripped from the Sagittarius dwarf galaxy, which is a satellite of the Milky Way. And this kind of shows us that Milky Way is still accreting satellites that we kind of want to understand how many there are and what they were like. And one way of doing this, not only for the currently disrupting satellites, but also ones in the past, is to kind of move from just spatial coordinates will be shown on the left to phase-based coordinates shown on the right. So this is an animation of what happens when a satellite galaxy comes into the approaches the Milky Way, and due to the Milky Way tidal forces, it gets stripped away and form these long tidal tails. And then on the left-hand side, I'm showing the disk size and the location of the sun as well. On the right-hand side, I'm showing the energy and angular momentum distribution of these galaxies. As you can see, that's I kind of added a couple of more to to see that as time goes on, they contribute to the buildup of the stellar halo. And after a while, kind of all of this debris mixes together in a way that if they weren't color coded, it would be really hard to say which from which event. However, in this space of energy and angular momentum, they are pretty well separated because these are the conserved quantities, or at least approximately so, if we assume that the gravitational potential is not changing very much and it is axis symmetric. So these are the two conserved quantities. And then the idea first presented by Amina Helmi more than 20 years ago was to actually measure these quantities and see what the stars in the Milky Way, how they behave in this space. And it took a while because they're hard measurements to make. We didn't need like the 60 phase space, so the 3D positions and the 3D velocities, but now we're there because we have calculated those orbits and can see what the actual data in the Milky Way looks like in this space.
Would you be kind to go to the previous slide?
Yeah.
For a second. So wouldn't that be a wonderful thing to put like constraint on the dark matter halo during near and like the close vicinity of the center of the Milky Way? Like using those orbits, can't you do that? Because I remember there were some speculations about one of the differences between CDM and SIDM is whether the halo, dark matter halo gets like more pushed towards the center or not. So,
Yeah, that's exactly right. This kind of orbital, or rather, the orbits are determined by the distribution of matter in the the gravitational potential. The issue with this particular data set is actually better shown here, is that we do our best to not observe close to the galactic center. Rather, so we really have nothing that comes close to the 5 kiloparsecs from the center of the galaxy.
I meant that. I think it was about 5 to 20 kpc from the center in the Z direction, like very close radially, but it's bad in the Z direction. So
yeah, so then depending on if that far away, my guess would be that you will get the strongest constraints by looking at the tracers that are within like a sphere of influence. I think that's like to resolve the core. It's maybe like a kiloparsec in size, I think, for like a SIDM halo in the Milky Way. So I think you would probably want to be closer into the center. But certainly part of like measuring all of this information in the outer halo is to measure the shape of it as well. So I would think that you would, like in this data set, you would get most constraint in the outer parts of the galaxy. But you should be able to use the same kind of machinery to constrain the inner shape of the inner part of it.
did you make it public, the data set yet, or no? Is it just...
So this is not yet public, but will become at some point. But if you want to, collaborate, let me know. We are our collaboration policy is that if someone wants to use the data for a well-defined project, we are always happy to share it. So if you have an idea how to use it, let me know.
Wonderful, thank you.
Awesome.
Okay, can I ask a question too?
Sure.
How uncertain are the orbits themselves?
Yeah, that's a great question. So obviously, right. So I mentioned what our precision is on the data side. There is a big caveat that we like to calculate the orbit. We have to assume something for the gravitational potential. And so I think to the bulk function, like kind of the bulk property. So we measure the total mass of the Milky Way, I think, fairly precisely. I think the mass of the disk is known pretty well too, but those are the kind of static components. And I think now a lot of the community is moving into measuring how much does the time evolution matter. For example, that the Large Magellanic Cloud has just kind of passed its first barycenter. And so those haven't been really included in these calculations. And again, I think it will depend on like which part of the galaxy that you're looking at. There's been a paper that's estimated, I guess, the impact of LMC on globular clusters. And so it looked like it was more of a 10% effect change in acceleration that it has. So if you can live with that, then that's kind of the order of magnitude, at least for the outer globular clusters. So yeah, I would say that kind of broad brush picture is probably fine, but for a lot of details, we would want to do better, which is part of why I'm kind of going through this exercise of trying to understand when the different building blocks, the different galaxies were created in the Milky Way, how massive they were, and how they impacted the radiation potential. Anyone else? Yes.
What about on the slide with the spectrum? I mean, now that one and the next one where you have the energy versus angular momentum plot.
Yes.
I mean, do you have some abundance information as well?
I do, and I will get to them
Okay.
very quickly. Yes. So, okay, this is a great segue. So I said this was just a simulation, kind of cartoon picture of what we expect. Here is the data, again, in the phase space. So this is, not with the actual numbers of axis. So this is from a couple of years ago. Our sample has grown in the meantime, but this is work from Rohan Naidu, who is a graduate, was a graduate student at Harvard, now is a Larda fellow at MIT. And so, yeah, he selected giant stars in our samples. You can see that we are doing our best to exclude the disk plane and not really going anywhere close to the galactic center, but then extending far out in the halo. And this in the spatial coordinates is pretty well mixed. But when you look at the phase space, you do see a certain clumps over here. And so the most massive one was discovered before as the last or debris from the last major merger of the Milky Way called the gas oxygen cell lattice, or GSC. And over here is the debris from the Sagittarius dwarf galaxy. And then when Rohan subtracted these major things, he found like a lot of lower mass structures as well. So much so that he could basically for every star in our sample produce a tag saying where it came from. And now to kind of just walk through this a little bit more, because over here you can see that many of these labels are overlapping even in this phase space diagram. But these are just some of the quantities we can plot. And if we plot some others, including eccentricity versus radius on the top, right, and then alpha over F versus Fe over H mineral abundances on the bottom, you can see how these different structures separate in these planes. So starting from the most massive one, this is the GSE shown in yellow. You can see that occupies these radial orbits over here. Very eccentric, which is a radial merger, and then fairly metal-rich. This is an interesting discovery. It looks like this was a fairly massive dwarf galaxy to be able to produce this amount of metals in such an early part of our galaxy's history. So once on the bottom, we'll keep track of kind of how much each component contributes at different radii from the galaxy. And so you can see that in the basically inner 20 kiloparsecs, most of the halo is this debris in this one event. The rest in the inner galaxy is are disk stars that have been kind of kicked up. So they have eccentricities that are kind of anywhere from circular to radial on top, but they're very metal rich and also often has, so they have basically the same metallicity as the disk. And then finally, we go to the third major component, which is a Sagittarius dwarf galaxy. You can see it occupies predominantly this upper left region of the diagram, is kind of metal rich, similar to GSD merger, but somewhat more metal lower in the element alpha abundances, which reflects kind of its later accretion time. And this basically, like these three structures, basically contribute to all of the halo stars within 50 kiloparsecs or sample. There are a smattering of smaller ones, like these structures that Rohan called retrograde shards, which are on this opposite side of the V structure of the phase space diagram, that have a widespread of metallicity. So we think there are actually three different structures. And once we add like the rest of them, you can see kind of that most of this space is accounted for. And so this point, it kind of can kind of look at the merger tree of the Milky Way and can kind of see what were the dwarf galaxies that formed it. Now we have really identified which were the kind of galaxies that brought the most mass onto or most stars and dark matter onto the Milky Way. And detailed studies like the one that I showed, we can kind of decompose them in their chemical abundances to study their detailed properties to learn more about the galaxies in the early universe that we cannot observe directly. So this was kind of composed to the first part of the talk here. But then the second part is one where I would transition into asking a question of how these galaxies have affected the Milky Way that was in place at the time of the merger. And so I touched a little bit upon this already, but the first clue that there was something happening came in the very first year of Gaia data, in 2017. We were looking at stars that had chemical abundances and orbit, like the very first set of orbits that we were able to measure. And this is for combining Gaia DR1 data with Raven apogee spectroscopy. And we kind of looking at the chemical space, we see that, so this is, alpha over Fe versus Fe over H again, abundances. So the scale to solar, such as the 00 is the location of the sun, and these are stars close to the sun. So most of them also have chemical abundances like the sun. So they live in this kind of island on the bottom. And when you took just 4 random stars from the sample and plot their orbits, you can see that they're mostly in like one plane, which is kind of what we know where the sun is moving. So expect all of the suns to sun-like stars to be moving on a singular orbit. Then when we take stars that are slightly more alpha enhanced, but still fairly metal-rich, we get pretty similar distribution of orbits, although they can get a little bit kind of higher above this midplane. So I think this is what we canonically call the thick disk. And then when we go all the way to the metal core stars, and we get stars that are kind of orbiting in a spherically kind of symmetric fashion. So this would be part of the halo. So this is all kind of what we expected. But then we also found another population of stars that are also on these kind of halo-like orbits extending far above the plane, but as they had chemical abundances like the thickness stars. And so this was like a big puzzle of how did they get there? And luckily, as many of you know here, because Dushan is here and runs like these very high resolution simulations of, well, galaxies in general, but in particular, Milky Way is the one that we use here from Fire Project M12Y. The simulated galaxies are becoming very realistic and allow us to compare them directly to the data. And so this is a selection of star particles from the this M12I simulation in a solar like neighborhood, like the one basically repeating the experiment I did for the Gaia data in 2017. The difference being that I could check where these stars were formed. So these are stars on halo or star particles on halo-like orbits. And I'm showing the formation distance on the y-axis and the age on the x-axis. And the color coding is by metallicity. And so the first thing to note is that indeed there are some of these halo-like stars that are fairly metal rich. And when you look at it where they formed, it looks like most of them formed in the inner part of the galaxy, some as close in as 1 kilometers. So it looks like there are kind of two modes of or two origins of stars, halo-like stars in the solar neighborhood. Ones that were accreted from the dwarf galaxy that formed far away from the center of the Milky Way, and those that were kind of formed in situ in the disk, the primordial disk of the Milky Way, and then were kind of picked out on these halo-like orbits. And so this was kind of, well, we wrote up the paper saying that this is likely the origin of these stars, but it was kind of really through this comparison with the simulation that we could make this conclusion. But then as we were getting better data, we were actually able to measure ages directly of stars in the H3 survey. And so this is kind of showing some work from a couple of years ago, where I'm showing the HR diagram, or well, I guess the astroseismic HR diagram of stars in H3 survey. So showing the surface gravity on the y-axis over here and the effective temperature on the x-axis. And the color coding is by age precision. And so you can see that for stars here close to the main sequence turn-up, where stars are kind of regional diagram, the stars are moving on the fastest, we get to age precision that is pretty good. And so just selecting this region of the diagram, I can get median age precision of 10%. Yes, our kind of extent of the sample is then very much limited to this maybe inner 5 kiloparsecs ago. But we thought this was kind of worthwhile, even though this is not getting like the full sample that we have kind of in Rohan's work. Still interesting to see what the distribution of ages is in these different components. And so this is now the distribution of ages in main sequence turn-up stars for the two components of the halo, the accreted metal core, which is shown in blue, and then the in situ metal rich component shown in red. And so you can see both are fairly old, but the in situ one, it looks like a couple of giga years younger. And interestingly, when we select stars with the same chemistry, but with disk orbits, they have the same distribution of ages, whereas these stars with lower alpha element balances, so more like the sun, are slightly younger. And so what we think happened, or that can explain this figure, this data, is that originally, like in the primordial Milky Way, something around 12 giga years ago, there was a separate dwarf galaxy, still kind of on its way to the Milky Way, and the Milky Way itself formed stars in like this very puffy thick disk. Then somewhere around 10 billion years ago, the dwarf galaxy merged, deposited some of its stars into the halo, kicked some of the existing Milky Way stars to the halo-like orbits, and then deposited the rest of its gas to form the new disk that is lower in alpha and slightly thinner, and so on and so on. And so this is showing that this one event, we think, has impacted the galaxy at these early times, 10 billion years ago, and we can still see the traces of this event even today.
Can I ask a question?
Yeah.
How do you get star formation rate?
Oh, yeah, sorry, this is maybe a little bit of a misnomer. Really, it's just scale, like just a number density of stars.
It's just like the number of stars at each different.
Yeah. It's just like scale such that the density is unity for like each component. Yeah. And so, right. So what I wanted to do, like going forward, is kind of see how this picture evolves. So I show how much we can learn from studying this one diagram, like the energy angular momentum phase space. And this is kind of the version that we use in Rohan's paper that had roughly 7,000 stars based on H3 spectra and dia DR2 proper motions. So then for a while, as I mentioned, we weren't able to operate the telescope due to the pandemic closures. But Gaia released a new set of the new reduction of proper motions based on a longer baseline. And so even though we didn't, like a year later or like 6 months later, we didn't add any new observations from the H3 survey, this diagram kind of became a little bit sharper because we had better Gaia proper motions. And then finally, this year, we started operations again. So we are now up to 13,000 stars in this diagram, and still like the improved Gaia proper motions. And it looks like there are some new structures popping in. So this is kind of a test of maybe how optimistic you are in identifying structures in this point clouds. But it looks like there are these ridges or ripples kind of extending from this left edge of the diagram. And if you squint really hard, you may be able to see some even in this kind of central part as well. And I get very curious about this because you usually think about structures in the spaces, we think like, oh, maybe that's just like a new dwarf galaxy. It looks like this is where we expect this stars to be. So this looks like it might be something different of what's happening here. And so I wanted to first convince ourselves that this is really not an artifact of some sort. So kind of sample the uncertainty. So showing the energy histograms by bootstrapping the distribution of halo stars on the top in blue and the stars in the bottom in red. So you can see as the kind of number of samples increases that we see these peaks becoming more and more prominent. So really signaling that there's some actual structure in the energy distribution of the stars and halo stars. And it looks like, even though, yeah, there's at least some correspondence as to the location of the peaks between the two samples. So this is very interesting because it feels like if there is something like these peaks are occurring at similar energies, both in the disk and the halo, there needs to be something external that cause both of these sets of kind of orbital resonances to form. So to check, still focusing just on the display, that these are actually, part of the same population, I'll show their chemical abundances. So for the four main ripples, from orange to purple, from bottom to top, and their chemical abundances will be shown on the right-hand side. So this is again alpha over T versus Fe over H. So you can see like in each of these, it looks like that we expect the most of the stars to be in this population of stars that look like this and have high alpha element abundances around at fairly high numbers. And we kind of extend to this ripple region, looks like they're largely overlapping this this island of like chemistries that signaling that they are actually a part of the same population. Yes.
I'm intrigued by the ones in the upper right-hand corner though, because they have high alpha elements. That's got to be coming from quark lab supernovae, and low iron, which means that's also consistent with being very young when the stars formed, right? The age was, they're very old. So when they formed, there hadn't been much time for type 1As. That's mostly where the iron comes from. So the iron had to come from quark labs as well.
Yes, I think that's correct.
There are lots of them.
Yes. Yes, there are, and there's like interesting, question. You can see like this. Some of this track also it's an interesting question how that formed. I think it's a little bit unsettled. We'll probably anyway, I think this just shows the potential to learn about yields.
For europium and that guy.
Not in the spectrum that we have, but some of these at least are fairly bright, so we could actually follow them. Yeah. I can check in and see. I think these are actually all. I probably just applied the high signal tone, like signal tone is higher than 10. So I would imagine these are bright enough that like we could measure Europe here. Yeah. But back to the question of kind of what caused this puzzle, I wanted to share the distribution of orbital periods because I kind of got thinking what could kind of shepherd stars towards the common energy levels, and the only thing I came up with is something like in the analog of a solar system, in the asteroid belt, where there's kind of mean motion resonances with Jupiter that kind of clears some of the energy levels, and I want to check if kind of this could be a similar situation over here. So showing on top is the distribution of periods, orbital periods for stars in the disk, and on the bottom the prograde halo. You can see some of the peaks, and some of them kind of overlap between the two populations, and the peaks in the disk at least correspond to the energy peaks, which is not surprising. But then what was surprising is when I overplotted the resonances with the Sagittarius orbit. So this is the top shows kind of which resonances there are. So this is 1 to 1, and then 1 to 2, 1 to 3, and so on. Looks like that many of them align with kind of like the gaps in this distribution of periods. And so I thought, okay, maybe it's worth seeing if something like an impact of Sagittarius could produce such a structure. So this is a movie I'll show over here. It's a movie of a very idealized model where we have all of the stars like in an infinitely thin disk. So they should be shown kind of in the inside over there, and then have Sagittarius kind of in a fixed potential orbiting for 5 billion years. And the main figure will show how the energy angular momentum of the distribution of stars evolves. You see as kind of in the second passage of Sagittarius, you can see this ripples start to form, and even though they kind of shift in energy levels depending on the exact phase of Sagittarius, they kind of look like the data which is shown on the right. So those is at least plausible that something like a Sagittarius impact could produce these ripples in the disk and then also affect the halo. And so this was I'm very excited about this because it gives us yet another handle to learn about the galaxy. And so just, I only have time a little bit. So just quickly show the dependence on the mass of the Sagittarius, kind of how like these experiments look like as we increase the mass of the Sagittarius. You can see that the size of these ripples kind of becomes, or the ripples become more prominent, and the shift in angular momentum becomes larger as we go from left to right. And then the second experiment, concerning Sagittarius, is changing its orbit. So what I'm varying here is really a distance to the Sagittarius, which in fact changes the eccentricity of its orbits, going from more circular on the left-hand side to the more elliptical on the right-hand side. You can see that that basically kind of shifts the location of these ripples up in energy, which also, so it looks like that from the combination of the two, where we actually observe the ripples and kind of their spacing, we can learn about the mass of the Sagittarius and also its past orbital history, which is really amazing given that this all happened kind of goes billion years in the past.
And are those just offset
Yeah,
for
yeah.
visual? Okay.
Yes, indeed. So these are, they will be all. Actually haven't checked how much. I would imagine they didn't check move too much overall. Maybe there'll be like slight shift, but most of the shift is just orbital.
How big is Sagittarius? Sorry, I don't have a number up like that.
Right. So here are the masses that I use. And I
Like dimension.
represented it just as a Poincare sphere. I think something like 7 kiloparsec scale radius. Yeah. It's just also like a very idealized scenario. It started out bigger and shed material.
What is this perihelia of passage when it's orbiting the moon?
Like 20-ish kiloparsecs.
We have plenty of like dark matter subhalos which are at that mass, that dimension, coming within that distance, don't they?
I would imagine, the Sagittarius brought in a lot of subhalos. Yes, obviously, like the Sagittarius itself, like that would be the most massive subhalo, but it would have yeah, many more. So it was order of 10 to the 10, probably the mass of the Sagittarius, and so it kind of probably holds on, well, yeah, the full mass function of the lower mass ones as well. Yeah. And finally, I think we can also use this structure to learn about the Milky Way itself. So this is one neat idea that was proposed by Robin Sanderson, was that we can use these structures in phase space to find the correct gravitational potential, in the sense that because we think that structures should be conserved in phase space, like the correct gravitational potential will produce this map of phase space that is the clumpiest. And so here I'm just showing the one projection, like the energy histogram for the disk stars in cases of our fiducial model of the Milky Way, which is at the center, and then a lower mass disk on top and a higher mass disk on the bottom. You can see that it might be a little bit slight, and we might want to actually quantify this, but it looks like these peaks are the most prominent in our fiducial mass, and become kind of less prominent and almost kind of washed out on this lower mass models or calculations of energies, assuming the lower mass Milky Way. So I think, yeah, it shows that like this can be yet another handle to learn about the potential of the Milky Way. And it's really exciting because there are a number of other studies showing that there's like a lot of perturbation that happened on the Milky Way. For example, this phase space spiral from a couple of years ago, but this is really mostly contained in the solar neighborhood. And the structures that we are now finding in H3, those are fairly, at least a couple of kiloparsecs beyond the galactic plane. So we think that the kind of dynamical memory of stars in that region of the galaxy is longer, and then we can reconstruct the dynamical history of the galaxy using features like that. And this is all tied back to our original question of kind of characterizing the environment of the Milky Way and making sure that kind of our laboratory, like we understand our laboratory well to ask the cosmological questions. I think it's really crucial because what awaits us is like this view of the Milky Way night sky that goes from SDSS level to LSST level, where we see all of these many stellar streams perturbed by potentially populations that are kind of sub-kilo all the way out to the real radius of the galaxy. And then we'll really want to have this information of kind of what our galaxy is currently and how it evolved to be able to decode this information. So with this, I will thank you and ask for any questions. Thanks. Yeah. Yeah.
Do any of the trajectories come anywhere near that star, and are they going too fast to be captured by it?
Ooh.
Mainly when you finish looking at the rest of the sky.
Yeah, that's an interesting question. So there is one stellar stream that is discovered kind of close to the center of the galaxy, and it's unusually short. So I think it has been affected by maybe the galactic bar. I think it might still be too far away from Sag A star. But in principle, there should be like a lot of tracers in inner part of the galaxy. Now people are discovering so many like small globular clusters in that region that must be also tidally dissolving as well. So I think, yeah, the current answer of no is really mainly because we haven't looked at it yet. And many actually, maybe I can go back
I
to
was
this.
just wondering if they could be the source of Andrea Getz's O-stars and stuff that are orbiting very close to the black hole.
That's an interesting question. So, yeah, I think it's a little bit harder because the accretion events that we are seeing now are, yeah, coming in like at larger, like higher energies and larger radii. So I think it would be hard for them to be that, but just to, bring this point from Bridget's plot, we actually haven't really searched this inner region, so there might be, some of them may be connecting as well, but we don't know yet.
So my question was, in the plot that you talked about the fire project,
Mhm.
we see some, what is it called, pattern of like the curved things, like
Mhm.
that you, if you know, like why, or like what is the reason behind that?
Yes, that's a really good catch. So those are actually individual satellite galaxies that are still forming stars as they're approaching the Milky Way. And so, for example, this one, you can see, in the simulation started at, I guess, 300 kiloparsecs from the main presenter, and then got closer, and then just, nothing happened.
Right.
So it got just disrupted. But this one, you can see that it came closer and then bounced back. So it actually wasn't disrupted on the first impulse, but it made the full circle, kind of came out and then came in again. And all this time was forming stars. So these are, what the tracks are basically. And it's actually interesting, like that you can see like this coincides with the stopping of the formation of the, formation. Stars that I identified as part of the halo that are formed in situ. But I think it's not coincidental, but it really needs something very massive to kind of kick these stars out, and nothing as massive came later in. So that's why there's no more kind of in situ stars formed later in the galaxy. But it's a great question.
Thank
Do you have any idea how long, like the time scale those space-based ripples might persist after a specific event?
That's a great question. Yeah, so the stars are old. These are all kind of these thickest like stars. Sagittarius first barycentric passage was 5 or 6 80 years ago. I guess all of my intuition is based on this movie. So it's which is to say, it's very early days in this research. It looks like it takes a little time, at least in this simulation to form the ripples. And there is some literature showing that the energy spacing between the different peaks corresponds to the time, such that it's kind of, if it's just kind of a single impulse, that with time these ripples will start getting closer and closer together. So I'm sure that this will be somewhat modified because Sagittarius is still surviving. So, it's a great question, and I think it warrants a numerical experiment to actually answer it.
I was just wondering if there's any, like, beyond just alpha over iron or something, is there any like finer scale abundance patterns that provide useful information here?
Yeah, so we're in this question really limited by so this is really all of our spectra, so there are not that many lines other than iron and magnesium, and we only were observing half an hour per targets, so which is really guaranteed that we get this velocity precision for at 18 magnitude. So which is to say that with these spectra, probably not, but we are working on a follow-up with a high resolution spectra for brighter stars, where Dr. George's group meeting a little bit, we had measured some, and this is work by Rokanaidu and LSG, the European and Varian abundances for a couple of dissolved dwarf galaxies, the most massive ones, and now it's like continuing work on the lower mass ones as well. So it's a lot, it's full of work, so it takes a little bit longer and not like in this survey mode, but it's coming. Yeah. Cool. If there are any elements that we should be paying attention to, I'll keep in touch.
Okay, I'm wondering about that phase diagram where the Sagittarius was causing like the phase bubble. Is that so it goes like up and down? So does that mean the Sagittarius is like orbiting the Milky Way still? And on the top right, there was like a little bar. Is that also kind of like the stars getting perturbed as?
Yeah,
uh,
yeah, exactly. So again, with the caveat, this is like very, very idealist. So yeah, the bouncing ball is basically okay, so the star is the Sagittarius, like the energy of the Sagittarius orbit, and then the bouncing ball is the potential energy of Sagittarius, because I just wanted to kind of have a visual cue of kind of how close Sagittarius gets to the disk, and it does correspond to the like this in the inset is showing kind of stars as a bar, which is kind of just looking at the disk edge on. And then as you see kind of Sagittarius coming in, like some of those stars get flung a little bit out. But so this gets a little bit puffier, but not like completely messed up, which is, okay, because we don't have this, we still have a disk that is pretty much a disk, even though there are some signs of perturbation. Yeah.
So, this question was kind of like asked earlier, but in one of the graphs you're plotting, I think it's like, alpha over iron and then iron over 100 or something. And it's like, talking like somebody asked about like where, I think it's President Fuller, he asked about like where those stars are coming from. Can you talk more about that?
Oh, sure. So maybe like in this diagram?
Yes.
Yeah. So so I guess how we think chemical enrichment proceeds is that start like somewhere way off the plot, and then core collapse supernovae produce some amount of iron but at a fairly high fraction of alpha elements, and so you're kind of moving like in this direction at first, but then supernova type 1a, after some time, which takes for the white dwarf to form and then explode, they start producing more iron and not much alpha elements. And so this kind of trend starts looking down. And this is basically it's probably like the best one I can show. So this is kind of, if you have a galaxy in isolation, this is kind of what you would expect happening. And in the Milky Way, this is, maybe this, I can show it on this diagram for the gas, sausage, and Enceladus. This is kind of like where most of the stars are in this dwarf galaxy, that we think that they kind of supernova type 1a started forming, and that's why we have like this downward slope. And it seems like the star formation was fairly efficient because it reached these fairly high metallicities, and like later I showed, we think that star formation stopped in 10 billion years ago. So it really isn't just 3 or so billion years managed to form this amount of alpha elements and then iron abundance. In the Milky Way itself, we think that the star formation was even more efficient, so that this downward slope started happening at even higher metallicity. So this is like this cloud over here, which is where we think that this primordial kind of thick disk population came from. And then a population that we don't really have much of in our sample, but is better visible in this sample from Apogee. Is okay, so sorry, I'm showing like the same diagram in different kinds of data. So in this data, here this would be this gas, sausage, and Enceladus track kind of going down at somewhat lower metallicity, and then this is the track of the Milky thick disk, which was kind of formed at a similar time, but in a more efficient way to start forming environments. So it enriched more in iron before in the same amount of time when supernova type 1a started forming. So this is why this downward slope happens at higher metallicity. And then it looks like that this kind of, like it didn't continue this way, but it actually kind of reset. And we think this is because the fresh gas was brought in by this gas-sausage Enceladus merger, which kind of reset the alpha element imbalances, like it kind of this location could be somewhat at the same alpha elements to be more metal poor. And then again, they start forming type 1a supernovae, which are giving more iron and kind of doing this track this way. So this is kind of a primer on the reading this sort of diagram. And actually, there's some work by in simulation by or fire simulations analyzed by Emily Cunningham, where she took dwarf galaxies that merged with the Milky Way and that simulation, and plotted each of them in this diagram and tried to find like separate templates to kind of use to decompose this observed structure into the individual kind of dwarf galaxy progenitors. And there was a question of kind of, this is like in these two elements, it's just like the simplest thing you can do. Like there's many more elements that you could try to track and kind of tease out the different processes. But it's kind of the general idea of using this space to kind of learn more about the dwarf galaxies themselves. And so, yeah.
Whenever we see these plots never have uncertainties on them, is that because they're smaller than the size of the dots?
No.
Oh, it's not. Okay. Like, especially because coming back to the question about orbits, like, and then you see the little ripples, like if you have some level of uncertainty, do those like get washed out a little bit, or the uncertainty is just so tiny that those ripples are really?
Okay, so for ripples, yeah, for the, okay, let me.
I know we're in the wrong place for that,
chemistry,
but yeah.
I guess.
This and also the
Could
dynamic
be
ones.
better about adding, like actually, error bars in all of these, figures, but for at least, the ripples, was kind of wanted to make sure that this is not like some artifact. And so this is why, in this diagram, I was basically resampling the observational uncertainties.
You are, okay.
Yeah, so for every star, and there's like an uncertainty in the 3D position and 3D velocity. So I sampled that and then calculated the energy and then plotted this like for all of them. And so this is 1,000 resamples for the two populations to actually make sure that these are not like some artifacts. Yeah.
And these two are like not super dependent on the orbit fits, is that right? Like they're actually just from the positions and the velocities, or they would rely on the or whatever.
Yeah, I mean the energy does rely on the assumed gravitational potential, and this like to some extent you can see it like in this diagram where I just change the mass of the disk. You can see that the more massive the disk or the more massive the galaxy, everything pushes to lower energy because it's kind of more bound, basically. Yeah.
Right, any other questions? Right, thank you very much, Annie. Guys, sticking around? Anyone else? Okay. Sticking around? Yeah. Thanks, everyone online.
That was a really beautiful talk. All your slides are so, the movie.